thank you very much for the invitation. Thank you for coming. I know you're here for the food, but I'll try to make it pleasant to you guys, okay? So I work full-time for Intel, specifically Intel Labs, and more specifically the Intel Parallel Computing Lab. And Intel established a center at MIT a few years back, in fact, almost 4 years now, with primary focus on big data. This is a big center. All these universities are kind of affiliated with this program. I'm one of the researchers based at MIT from Intel, and I've been here for 3 years, and during which time I built TileDB. TileDB is just one of the projects of this ISTC. There are many other interesting stuff there. If you're interested, you can check it out. We have online all the information. So today I'm going to focus only on TileDB. All right, so this is the outline. First of all, I'm going to explain the basic ideas on TileDB. Then I'm going to tell you about the specific use case we have for genomics, and we have been working with Eric Banks on this, and I'll tell you exactly what we have done in this area. And then I'm gonna tell you about the future, and this is probably most interesting to me, what we're actually building and where we're taking TileDB to. Finally, I'm gonna tell you about the people involved in this project. So what is TileDB? So TileDB is a system that manages multidimensional arrays. This is the most generic interpretation that I can give about TileDB. And I'm going to spend some time on explaining the general array model. This is general. This has nothing to do specifically with TileDB. There are other systems that try to target the same model. But this is general enough, and this can capture a lot of applications, not only genomics. All right? So this is the specific case of a two-dimensional array. So these are matrices. We have a dense matrix and then a sparse matrix. And we differentiate between the two. This is very important for TileDB and other applications as well. It's important to differentiate between the two because there are different algorithms devised on either of these categories and a different representation on the disk. So it's important. So a dense array is characterized by the fact that every cell, every element, I call it a cell, has a value. Even if it is 0 or null, we must put something there. This is a dense array. On the contrary, a sparse array may have empty cells, and we store nothing about these empty cells. This is important. Now, we have dimensions. Obviously, in this case, we have 2 dimensions. We can have as many as you like. We can name them, and each dimension has a domain. The domain could be an integer value. It could also be float in the case of sparse arrays in TileDB specifically. Not too many systems can do this. But the domain could be ints, floats of variable length, of variable precision, okay? Now, in every cell, we can store tuples. So we depart a little bit from standard linear algebra where we have, for example, floats or doubles there. You can store whatever you like there. Okay, so there are tuples. And each value or each tuple consists of multiple attributes, as in traditional relational databases, right? Every A1, A2, etc., these are attributes. And each attribute has a different type. It could be anything. Ints, floats, characters, or variable size. You can put whatever you want here. So this is the main idea. This is the model. This is a general model. Once again, multiple applications can be captured by this. All right. The most important thing in TileDB is probably the global cell order. Now, TileDB is devised so that it can store efficiently multidimensional arrays on the disk. Why is that? Because the data we're targeting at are huge. All right, even if you have multiple machines, even if you have collective DRAMs and big quantities, the data we're targeting at exceed those. Okay, so we do need to have a very effective representation on the disk. However, although the data model is multidimensional here, the disk is single dimensional. You need to serialize the bits somehow on a serial medium like the disk. All right, and this poses the biggest challenge because we cannot do it randomly. We cannot randomly store the data on the disk. So this global order essentially maps the multidimensional cells to a single dimensional order. Okay? And obviously, you need to define the order in a way that localizes cells such that they retain their spatial locality. And this depends on your application. Depending on your access patterns, the way you access the data, you need to store the data perhaps differently. So here, for example, we have the notion of these space tiles. Essentially, these space tiles, you can think of them as chunks in HDF5, or there are other representations as well. It's essentially a group of cells, and this group of cells goes together on the disk. All right, so one cell from here cannot be after a cell from here, for example. And then within every space tile, you impose a particular order. So here, let's take this example is better. We have a cell order within each tile. This is row major. And then we have an order across the tiles. And this is row major as well. So essentially, in order to impose a global cell order, you need three things. First, define these space tiles. So group them, group the cells together based on how you imagine to access them. Then define a cell order within a space tile, and then define a tile order across the tiles. And with this, you have a lot of flexibility. You can define multiple orders. All right? So this gives you a lot of flexibility in how you store data on the disk, essentially. All right, for the sparse case, the situation is very similar. Again, you have these space tiles, which are the blue rectangles. Again, you define a row major order and, you define a cell order and the tile order. But here, I have to emphasize on the following. In the case of sparse, we need to define another concept, which is called here data tile. That's the actual tile that TileDB gets its name from. So the idea is the following. Suppose that we have a dense array, and we want to somehow group cells together. And we make this group, for example, the atomic unit of compression, or the atomic unit of retrieval from the disk, or the atomic unit of computation. In the case of dense arrays, we have a perfect balance with respect to the sizes of each tile, right? Because every tile has the same number of values in it, because we materialize all values. The same is not true in the sparse case. Imagine if one tile, with this regular tiling, if one tile has one cell and another has 1 million, we cannot consider them as atomic units of compute or of compression, because there's going to be a huge load imbalance, and this is going to lead to so many problems when we do parallel computation or distributed computation. So here we do something very simple. We do group cells, non-empty cells, into tiles by defining a specific capacity for a data tile. For example, here we say 2 cells. Every data tile is going to have exactly 2 cells. So what do? We sort the non-empty cells. The empty cells we don't care about. We sort them in the order, in the global order we defined, and then we chop them. We say these two, so we traverse essentially this curve. We say these two go together. Let's create a data tile. Then another 2 follow. This is another data tile, and so on and so forth. This allows us to have data tiles of exactly the same capacity to load balance this atomic unit of whatever you define. Compression, compute, retrieval, and so on and so forth. And that's why these black data tiles seem irregular in space, but they have the same size on the disk. All right, this is a very important concept. All right, so what is the physical organization of TileDB arrays on the disk? So for the dense arrays, we do, again, something very simple. So if you remember, we have 2 attributes here. These are integers, and these are strings. So we do the following. For fixed-sized attributes like integers, we take all these values, we follow the curve on the global order. Here it's row major inside the tile, row major across the tiles. So the numbers essentially indicate, they imply the actual order, the position in the order of each cell. So we take all of those and we put them in a separate binary file. serialized across the order. This is a separate file, okay, and this is important. Now, for the strings, we put them again following the order A, B, B, C, 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 and so on and so forth in another file. But since this is of variable length, we don't know exactly how to chop the cells, so we need an auxiliary file that essentially defines the starting positions of every cell string. And that's it. But it's important to understand that these are separate files. It's like a columnar representation if you know about databases. All right? And this is important because usually we subset on the attributes we want to compute on. We do, for example, an average only on this. Well, then we scan only this file. We leave outside the rest of information because it's redundant. And this saves us a lot of time. Also, since we're compressing, as I'm going to explain very soon, compressing values of the same type is much better than compressing random things together. All right? So this leads to much better compression on a file basis. All right? And indeed, an array is essentially a folder on the disk. This is another subfolder. This is what we call a fragment. I'm going to talk about this very soon. It has to do with updates. And then each fragment has all this information I explained, plus some auxiliary other files. All right? For the sparse case, we do exactly the same thing. The only difference is this file. So this is a special file which essentially keeps the indices called coordinates of all the non-empty cells in the corresponding order. So this corresponds to this value and to this value. So always on the global order, we are explicitly stating which indices are non-empty. All right? This is important for searching. So far, so good? All right, now let's talk about the notion of fragments. This is very important because this solved a lot of problems that perhaps you had with your experience with HDF5, for example, right? The stuff I'm going to explain right now leads to rapid updates in TileDB. So in TileDB, you can do, for example, for this particular case, for the dense case, the sparse case is very similar. You can do two types of updates. You can update a dense subarea, for example, this entire subarea which is dense, or you can do random sparse updates. Either way. Essentially, the way TileDB handles this is that it takes these values and it perceives this as a separate array and therefore a separate subfolder over here. It's going to be a separate subfolder. Nothing is touched over here yet. We do nothing here. We're just appending this information, and I'm going to tell you how we handle it very soon. And this is a dense array, so it's super efficient to store this as an update. Now, for the random updates, once again, this is perceived as a separate sparse array. Although this was dense, this is perceived as sparse. Okay? And again, this is another subfolder. Now, where is the challenge? Because this leads to rapid updates. So where is the challenge? The challenge is in reading. Because when we read, essentially we have these three fragments, and the logical view is this. This is what the read is going to focus on. But it's going to operate on these fragments. And this is where we have a very nice algorithm for doing this very, very efficiently by not searching on every array separately. For example, if we're searching for this area, we will never retrieve those because the algorithm knows that this overrides this, so it will never go here. That's the intuition. It's much more complicated than this, but the read algorithm is the challenge here and the novelty in TileDB. Because this is kind of straightforward. The problem is here. And we have super efficient reads because of this algorithm. All right, so what are the summary of the features? This just touches the surface, right? We do have rapid reads and writes. This is a fact. We also have a paper at VLDB. This is one of the top database conferences where we have all the results. We have very exhaustive benchmarking there. We do have parallelism with both thread safety and process safety. So TileDB is multi-threaded, but TileDB is also works for multiple processes if you're familiar with MPI, for example. Also, we do have a consolidation technique which essentially takes these and consolidates them into one array like this. And the good thing about this is that it can work in the background while allowing other reads and writes, and then only when no reads and writes are there, the consolidated array becomes visible to you, and the previous fragments are deleted. All right? So this is good because it doesn't affect the operation of the system. Whenever it's ready, it just gives you the new array. So we have multiple ways. This is for more of a hacker type of users. We have different ways to access the data, like POSIX reads, we have memory maps, we have MPI/IO. So depending on the kind of disk you have, for example, and the kind of environment you can play with this, and they do lead to different performance. So it's good to know this if you're really striving for performance. We do have asynchronous I/O. This is very important if you want to overlap I/O with computation. This is one of the important features of TileDB. And finally, something we don't advertise that much, we do have a metadata structure which functions like a key value store. And the interesting thing about it is that this key value store is implemented with sparse arrays. Okay, I can get into this offline, but this is the interesting thing about it. However, so far, this discussion has been on the storage manager, and this is just a C library. You can find more information here. Everything is open source, but this is a storage manager. So you can imagine that this works like HDF5 right now. I'm going to talk about the future later, what we want to do. So how about performance? Well, we have heavily benchmarked versus HDF5, SciDB, which is an array database system, and Vertica. Vertica is a column store database. And we have all the results here. You can find them online. Or you can just contact me. I'm going to send you the paper. The paper is already public. The takeaways are the following. We are up to 4 times faster than HDF5 for the dense arrays. The HDF5 does not support sparse arrays. And this is important because this is a very solid software. This has been optimized heavily for the past 30 years. So this is solid. We are orders of magnitude better than HDF5 for random writes. The reason is that the random writes are handled as sparse arrays. HDF5 doesn't support sparse arrays. So this is kind of important in case you have such applications. We're orders of magnitude better than SciDB, and this is because TileDB is built on high-performance computing principles. SciDB adopts a lot from relational databases, so there is a big gap in performance right there. And finally, we're up to 40 times faster than Vertica for dense arrays. The reason is that when you have dense arrays, you don't materialize the indices, whereas in a relational database, you have to put a key. So the keys are the indices, essentially. And this gives a huge speed up. All right. Now, how did we leverage TileDB in genomics? That's the main question here. So I am going to present an oversimplified description of a particular problem you used to have here at the Broad, and of course in the genetics genomics domains. Again, this is my view as a data engineer, essentially, as a data scientist, right? And it's good to perceive it like this, because after abstracting a lot of details, the problem becomes very clear. So a DNA sequence consists of about 3 billion base pairs, right? This is very expensive to store. Of course, you attach a lot of other information with every base pair. So what do? There is a particular DNA sequence which is selected as the reference genome, and essentially every other sample, we kind of diff it after a big pipeline and a lot of filtering and quality analysis and everything. At the end of the day, we just store the variants for the GBCF format. All right, so I'm going to focus only on the GBCF format. This is what we have been working on with Eric Banks for the past couple of years. So the GBCF file, in my view, looks like this. There is a chromosome, or every line is a variant, or it is a range which says there is nothing there, or it's similar to the reference genome, essentially. This is, in my eyes, that's the oversimplified description. So you have a chromosome and position, you have an out value, you have a ref value, so this is the alternative, then you have the reference, and then you have a lot of other fields. All right, but this is my view. And this is for one sample. I'm talking about the initial GVCF files, not the combined. The truth is that this GVCF is much smaller than, well, the band file, for example, right? And even for the whole genome. We played a lot with whole exomes, but we also played with whole genomes as well. All right, so what is the query model? One of the basic operations, again, oversimplified, is across many samples, meaning across, let's say, 200,000 GVCF files, for a particular position, which I know, grab all the information you can see on all these files, and I'm going to perform a statistic on this. That's a very basic operation. You can materialize the details in your applications, and every application may have different statistics there. But this is the most basic thing. So what is the naive solution? Keep the 100 files or 200 files as they are, and just go to each of them and grab the information. This is going to be an overkill. All right, we have a lot of random accesses on the disk. These have to be on the disk. They're too huge to hold them in main memory. This doesn't work. All right, so what was the previous solution from GATK? And that was like a couple of years ago. And this is what we're trying to substitute, right? So the idea is to merge all these GVCF files. Just create one file, and then each line is going to contain a range or a particular SNP or indel for all the genomes, right? So every line, instead of corresponding to one sample, now it corresponds to all the samples. So if you do this, then there is a single lookup needed to find that entry, and then with a sequential scan, you get the entire row, you get information about all the samples. This is rapid. This is super efficient. The problem is that the storage and computation scales super linearly in the number of samples when you merge. When you merge, you don't get the union of the sum of the sizes. You get something that is super linear. With whole exomes, this is aggravated. This is even worse for exomes. All right, so this does not scale very well. So what did we do in TileDB? We do not merge the GVCF files. We understand that there is legacy code and everything. We have solutions for this. But don't merge the GVCF files. You can just mimic the access to this merged, combined GVCF file. We can mimic all the API. So how do we do it? We model the entire problem as a two-dimensional array, as a matrix. The rows are the samples, so I transpose a little bit the combined GVCF file. I like to perceive it like this. And here, the other axes are the positions. So there are 3 billion of those here. Remember, this is a super sparse matrix. I don't materialize every position. The only thing that I materialize here is a range. That's a GVCF range. That's a single entry in a single GVCF file. So the GVCF file runs like this. And not only that, but I'm just storing the end position, not the start. The start goes in a different attribute. But as a non-empty cell, the coordinates are specified by this GVCF sample and the end coordinate only. And this is the logical view. All right, this is what I do so far. Also, I'm storing these values in a column major order like this. This is also important. And TileDB supports this. So when a query comes, suppose that the query says, for this particular position, give me everything, all the ranges in the GVCF files that it intersects. So what do we have to do? Right now, if I just do this query, I will find nothing in TileDB. This is empty space here. I'll find nothing. What am I going to do? I have implemented an iterator which essentially takes this and scans it. And I'm going to scan until I find the first end position after the line for all the rows of concern. So I'm going to find this. This is the result. I'm going to explain why. Then I'm going to find this. Then I'm going to find this. Then I'm going to find this. And I'm done for these 4 rows. So how do I check if it is a result? First, I get this. Then I check the start position, which I have materialized elsewhere. and I see that this is before my query start point. So it intersects it. Now, why is this efficient? Because these are stored in column major order. These are contiguous on the disk. I do this with a single scan, and it turns out that the distribution of those in the real data sets that I played with from here is kind of uniform, which means that these rows are going to be filled up very fast. And this is true. This scan finishes rapidly, and it's a linear scan. So this operation is extremely efficient, and this is used for another purpose. This is used to create essentially this combined GDCF file on the fly from this array. This is what we're doing for the purposes of legacy code right now. So we are substituting GATK's algorithm with this algorithm, which just scans like this and generates the combined GDCF file. If you don't want to generate the combined GDCF file, you just need this database, and you just query, and this is going to be given to you very fast. If you want to do selected positions instead of everything. All right, so what is the current state? TileDB is in production, and this is called Genomics DB here. Because this is a layer built on top of TileDB. This is the Genomics DB that is being used in production, essentially to create this file. And we have some very big performance gains there. We're currently also integrating TileDB with GATK. We're working with a couple of people here. Please talk to these two guys. And Paolo is around here very often because these are the ones that are handling the Genomics DB parts. And you can find more information about this last chapter here, about the application of genomics. So far, so good? All right, so let me tell you very briefly about another application because, again, on genomics, because as I said, TileDB is kind of generic, it can be applied for other stuff as well. And I'm going to explain a dense case now. That was a sparse case. So I'm pretty sure you're familiar with Plink. Plink is a very optimized software. I have to admit it is a very optimized software, which essentially does the following. It has some genotype information. And this genotype information is stored in these bed files in a very compact way. Essentially for every genotype, for every SNP, for every person, essentially, they keep just two bits. All right, because there are 4 possible values to store there. All right, and the BIM and FAM files are some kind of indexing information. It tells you which genotype corresponds to which SNP and then to which person, more or less, or to which family. This is the main idea. So these are just indexing information. So how do we go from there to TileDB and why? So first of all, this is the bed file. I put it here in a dense array, 2 bits in each cell. It's as simple as this. In some order, probably the order is going to be like this, SNP major order, but you can think of other orders as well if you want to. Now, this one is this axis is the BIM file. Essentially, I attach a metadata structure to go from essentially from a SNP name to a particular position in my array. These are like the 3 billion positions. In fact, for this file, each position corresponds to a SNP in the bed file. All right? And this is the FAM file. I attach another axis, another metadata structure, which takes me from a particular person to a particular entry here. So I can start accessing this. So why do we do this? The reason why we do this, one of the reasons is that we can impose extra compression on this. This is something that Plink does not do. For example, remember that I had this data tile, right? And this is the atomic unit of compression in TileDB. So I can chunk the data like this or vertically like this. It depends on the access patterns. And then impose extra compression on top, and I get 4 times smaller files on top of Plink's compression. All right? And of course, in the future, as I'm going to explain, TileDB is going to be a big platform which is going to have an execution engine where you're going to be able to do a lot of fancy stuff. You can just link this to the engine, then you can do all the fancy stuff. You can do logistic regression, you can do other linear algebra stuff if you want.
How do you compress bits to less than bits?
It depends on the distribution, right? For example, here, most of them in a tile could be homozygotes.
But so the point is that you have a contiguous set of bits. Which
correct. So I'll give you an example. Suppose that homozygotes is 1, 0. This is how Plink, for example, is doing it. I'm not sure if it's 1, 0. Let's suppose it's 1, 0. And suppose in this tile, it's 1, 0, 1, 0, 1, 0, 1, 0, repeated 1,000 times.
Run length encoding.
I use gzip. You can use run length encoding. The truth is that gzip is doing a great job there. So it finds these patterns. If they were completely random, gzip is going to bring you nothing. You may lose a bit. But it turns out, I played with several files. This is what we get on the average, which is good. Yes?
Did you have to optimize the order of the samples or the order of the
No, we just left it as it was for now. So essentially, we tiled like this. This is a good question. We need to play to see. In fact, I wouldn't choose the tiling based on the compression. I would choose it based on the access pattern. For example, if you just want all the information across samples for a snap, I would tile like this, right? So that I do not decompress redundant stuff. I'm sorry. But on the other hand, if you somehow segmented also the population, and you said, okay, I just need these ones, like these samples, and only a couple of snips, I would tile rectangularly. All right? Okay, so how about the future? So, and this is my take. Okay, this is my personal take on this. TileDB is handling multidimensional arrays, and most of the scientific data we're targeting at, genomics, in finance also, in imaging, in graphs, I can model this data as multidimensional arrays. All right? So what is the need for these multidimensional arrays? Number one is linear algebra. It turns out this is super important for most of our applications. Also, fault tolerance, because if we scale to a lot of machines, it's good to have it. All right? So fault tolerance, I have to admit, is important. Cloud deployment for some, not for all people, not for all of our users, but several of our users are asking for it. And finally, programmability, because I can solve these problems for you, meaning the dirty problems, how to store the data on the disk, how to partition them across the machines, how to make the machines communicate efficiently, how to do fault tolerance. I can solve these problems for you, but at the end of the day, you are the ones that are going to build the models on top. So you need to have an environment to program what you want to do. TileDB is going to take care of the rest. So programmability is super important. And you must have, flexibility to be creative with your models. Now, let's discuss a few, let's say the status quo, right? So, coming from an HPC world, you do have HPC libraries. They have been around for decades. And by HPC libraries, I'm talking about very efficient linear algebra packages. They have been around for a while, and they have awesome performance. They optimize for modern hardware, so they're good to have them. Ideal, if we could use them, we would. Now, what is the problem? They don't have fault tolerance. This is an inherent problem also of MPI. They use MPI a lot. They are not targeted at the cloud. They're targeted at supercomputers. And programmability, you need to be a guru. You need to really be into this. You need to write in C. You need to understand parallel programming the way they do. So programmability is not their strength right now for us, let's say, for practitioners. Now, on the other hand, you have Spark and MLlib. And this is awesome. A lot of people love it, and they should, because MLlib provides you some of the functionality you need. You have fault tolerance. It's a very robust system. You have the cloud deployment, and you do have programmability. At least if you get to know it, things can become easy. And this is a personal statement I'm going to make right now. In performance, you see this. Performance is the way I perceive it as an HPC person. All right? This provides scalability. Scalability is not performance. Scalability means that you're willing to pay more machines on the cloud, and you get the speed up. The question is, can you do the same job with fewer machines? And this is where HPC comes. All right? There is a lot of work being done here. They're improving a lot of stuff. The basic problems here are the first, for linear algebra, it's difficult to model everything under a MapReduce model. In HPC, they do it with arbitrary communication across the machines. It's a different level of sophistication. The second thing is that Spark requires massive main memory. We have out-of-core computation. So TileDB is trying to do this. This is the future, right? This is under the future chapter. So how are we planning to do this? And this is gonna finish my talk. So first of all, this is indisputable now. We have proven this. We have a paper on this. We do have perhaps the best array storage manager out there right now for both dense and sparse arrays. So this is solved. This is done already. Our next step is to integrate with HPC libraries. We don't want to rewrite the libraries in a MapReduce style. We want to use HPC style libraries. Next, we are doing out-of-core computation. This means that your memory requirements are very small. This translates to money savings if you're going on the cloud. It's going to be cheaper. We will strive for a Python interface, and then we may link you to R and Julia. We will try to do fault tolerance. This is going to be of secondary priority because for our use cases, like, for example, several companies can afford, let's say, 50 to 100 machines on the cloud. Fault tolerance is not that needed for 100 machines. If you go to 10,000 machines, it is a must. We're going to use a shared nothing architecture. Forget about HDFS. We're not using HDFS. This is a shared nothing architecture. Local storage. We localize computation to the machines. Nothing is shuffled unless it is necessary. This is an SPMD. This is for the parallel programming guys. I'm not going to spend time here. Locality-aware task scheduling. This is very different from Spark. Spark does data parallelism. We're doing task parallelism. And then we have all sorts of optimizations. And this is because we're very close to the hardware. So we want to do vectorization for the modern Intel hardware. We want to do code generation to avoid complicated loops so that the compiler vectorizes properly. And finally, we are going to be using FPGAs and several other cutting-edge technology from Intel. This is the future. This is the goal. Now, if we achieve it, we will see. But we just set the standard. This is the standard. All right. And this is the promise. All right. We want people to do HPC programming, but without all the peculiarities of the HPC community. It is a little bit more difficult to code the way they do. And with that, this is the team. We have been working with a lot of great people. You can reach out to practically any of those because they're very well aware of what we're doing. And these are the folks from your side. Fine. Thank you very much. Please.
All the way at the beginning, you were talking about the institution of data structures. And, hey, you even have a mic. Wow, is this new? That's cool. So it reminded me of an almost like kind of like you're storing diffs as people update and write, and it almost feels a little Git-like. And the question that kind of begs itself is, can you branch and merge, right? And in order to parallelize and keep data localized, is there a way to merge disparate asynchronous updates?
Yeah, this is a good question. I know where you were taking this. So Git allows you to have multiple versions and do merges across the multiple versions, right? In arbitrary ways. What we have in our to-do list is to be able to go back in time. So this is like this versioning control, and this is called time traveling in our world. We will try to give it as an option. Now, I haven't thought about the arbitrary merges. I don't know perhaps what the application you have in mind. This would be very interesting. I don't believe it's difficult to achieve. It's going to be tedious. It requires development time. I don't believe it's a fundamentally difficult problem. It's just tedious. If we see that applications require it, we can do this. The good thing is that by having these multiple directories, essentially you can subset arbitrarily. You can say, I want only the updates that happened at that time, and that time. And then you can just, the read is gonna work as it is, actually. I can do, let's say, 20 lines of coding in order to get this working with arbitrary selections of times. But this arbitrary merges is a good idea. I don't know if we ever managed to do it.
So, if you have a database like one of these sets of GBCS that have been merged, what if something happens where maybe consent changes and someone would like to have their records removed, and so now you have to go and remove records? Is that something that we can do?
Oh yeah, deletions are supported already. You just say delete this line. Yeah, you can do it. You can even do it now. The read is going to take this into account. It's not going to return it. And when you collapse, essentially you will see a database as if that was never there.
But you have to rebuild the whole thing.
No, this is the consolidation process. If you just want to delete, this is going to be essentially one entry that is going to be appended in the directory. So this is going to complete in 1 millisecond, for example, truly. The read is going to continue working. If you do multiple deletions like this, the read performance may deteriorate a bit, up to a point where you decide that, hey, my read performance is not very good, I need to collapse them. And you collapse them in the background. This is not exactly as rebuilding, because you have a particular ordering. It's like merging. That's the good stuff. The global order enables you to do a merge operation rather than resorting.
You said that you hoped TileDB would be do everything plus performance, right?
Correct.
And one of those things that was part of the everything was cloud, but I don't see cloud there, and so I'm having a hard time visualizing how it all fits together.
Good. Everything I'm explaining here, for example, the shared nothing architecture, implies multiple machines. Shared nothing means that I have multiple machines. Each machine has its local storage, an efficient file system locally. There is no central file system, which means that you have to be very careful about how you dispatch computation to each machine. So you need a parallel, a distributed platform in order to afford this. It's going to take a lot of development time for this. I'm just going to mention it. With Spark, for example, you have it already. So it's only natural to use Spark right now. You have to. This is going to take more time. This is what we lose. We have all these great things, so what do we lose? We lose development time. Like, it takes me a lot of time to develop this. Now, as I said, this has to do with distributed computation. The cloud deployment is kind of an easy way for you to rent the machines and get everything started. So this will be designed for on-prem, and then to take it to the cloud, it's going to be trivial. There is a reason why. Because I'm going to use bare metal machines. This shared nothing architecture implies I'm going to do away with HDFS. Also, something that I haven't said here is the resource management. I'm going to do this myself. I don't want to leave this to other software that the cloud is using. So imagine that when I go to AWS, I'm just going to rent bare metal with Linux and local file system, and that's it. Everything else will be done by me. The deployment is going to be done by me. That's the reason why going to the actual cloud from a private cluster is trivial. Otherwise, we would have to figure out about an object store and how to be able to merge everything together. We're not going to be doing this.
In other words, you believe that this will leverage. In other words, you believe this will leverage a far greater supply of existing legacy code than object stores would.
I haven't talked about legacy code. No, a lot of stuff will have to be rewritten. You mean from the TileDB side?
No,
or from other people?
If, for example, you put this underneath BLAS,
correct.
I wouldn't have to change anything in all my top-level code that uses BLAS, right? I just make my BLAS calls, and if this is somehow underneath that,
correct.
then, so that's a win. Because
correct.
object
BLAS
store,
for sure.
you can't say that for object store. Such a
correct. And excellent. I got it now. Not only BLAS, even the other HPC libraries we're going to be integrating with. dPlasma, or you name it, because TileDB is going to run on MPI. These libraries, not BLAS. BLAS is just for the local computation, right? But the libraries built on top of BLAS, for example, for distributed computing, these use MPI. In order to do this in Spark, you need to hack it a bit. I know that people, even from Intel, are trying to do this, so I assume it can be done. For the cloud, I'm not sure. We have had our problems with, I think, with Google Cloud making this work. I think it can be done, though. It can be done. It requires more coding. For our case, it's going to run on MPI. We will invoke these libraries, and we're going to play very well with them. Yeah, please.
In your example where you had the sparse arrays, if the data cells start filling up, is there a redistribution of the, because a cell could, you said your data cells were like made up of 2 in your example. If I start writing more data and those data cells get 4 and some get...
Attributes.
Yeah, well, no, the contents of the cells.
The contents. Okay, excellent. This is trivial to handle as follows. I have to go a little bit back. I'm sorry about this.
I was going to ask it then, but you were going so fast. I said, oh, I'll let you finish.
Sure. I'm sorry about that. Okay, take a look at this, for example, right? So what you're saying is, what if I want to put more stuff here?
In the sparse cells.
Okay.
Yeah.
If it is in the empty, we do this. You don't change. So let's focus on this. That's my initial.
I understand the fragments get applied, but if that cell is no longer, you have it broken up by like 2, you try to balance your data cells by the equal number of elements. As I fill the sparse, that balancing gets off.
So suppose this is my original one. The distribution I'm going to do based on the capacity, let's say the capacity is 2, I'm going to do 1 tile here and 1 tile here, right? Suppose 1 more cell comes here, or let's say 2 for the sake of this example. Suppose it's these 2. I'm going to create a completely different array. This is not touched whatsoever. And these new 2 cells will comprise the new tile. So that's why this you just forget about it when you do insertions. So you still have a balanced number of cells per tile in the new array.
And it may be on a different system.
It could be on the same system if you want to.
The sort of boundary that you define.
Correct. If we depending on how we partition across machines, that's a different story. But yes. But the main idea is that this is not touched. Now, if you consolidate, the first cell may go and partner with another cell. So this is the redistribution you're talking about. But the good news is that after you merge, you have a global order, right? So how do we pack the cells into tiles? By just traversing the order and cutting in proper places. So it's not like reinserting or shuffling data around. It's mostly scans that we do. Yes?
How?
Thanks. Get turned on. I had it turned on.
How careful do you have to be about when you do that consolidation? Like, you know, do you have, is that something you want to kind of track and kind of take statistics on, like measure, like, you know, and you're going to lose, you're possibly going to lose your history if you do that. So like, you know,
excellent.
What are those considerations?
This is an excellent question for 2 reasons. First, when do you consolidate? Super important. Second, are you going to lose the history? So this captures all the, not problems, the issues you need to address in consolidation, these 2. First, for when you do essentially consolidation, we want to address this automatically. We do have a couple of ideas. We don't have the resources to implement. For example, what I would do, I would hold some statistics and see if the tiles across fragments overlap. A tile is essentially this, right? Remember? It's a hyperrectangle, which is tight, so that it includes only these 2. The tightest hyperrectangle that includes these 2, right? Now, if I see that in multiple fragments I have overlaps, this means that when I query this area, I need to go to all these and open them and do the merge, because I don't know what each tile contains, right? So I would assume, this is a heuristic that I would use, that if you have a lot of overlaps, at least consolidate that area. I would even consolidate that area. And I would patch this area with empties, for example, and say, okay, because the read algorithm acts like this, it performs like this. If you have a patch of dense empty cells, and on top you put some sparse, this dense area is going to completely overwrite the history, so you could never go to the other fragments, even if there are 1 million of those. But this is about when we consolidate. We will work on this. Otherwise, you need to keep track of your performance and say, okay, the performance has deteriorated after 1,000 fragments, or let me just compact them. For the history, yes, you're going to lose them. Unless, there, again, we can be tedious there and say, okay, after we consolidate, we keep somewhere else the history, and people can still time travel. It's not a fundamental problem, but it will become very tedious very fast.
Any other questions? All right, well, let's thank our speaker once again.
All right, thank you.